All right, let's get started. Thank you so much for joining IWC's second webinar in a recurring series we're calling Wired for Success. Now, today's webinar is entitled Wire and Cables 101 for Purchasing and Sales Professionals. And that's precisely what we have in store for you. It's really a primer on some of the basics of the electrical nature of wires and cables, and it's intended to help bolster your understanding for those of you who maybe are new to purchasing or sales roles in this industry and are just eager to better understand the nature of these materials. Now, my name is Dave Burleton. I'm the marketing leader here at IWC, and I'm excited to be with you today, and I'll be serving as the moderator for this session. Now, I'm joined today by our presenter, Matt Herbers, who's the Director of Business Development here at IWC. Now, in that role, Matt has visited hundreds of cable factories around the globe, and currently, he spends a lot of his time matching the application to the supplier resources for our customers. Now, in addition, he heads up the technical training program within IWC, so he's excited to share some of those same training materials with you here today. Now, Matt's a proud alumnus of Northwestern University. He has more than 30 years experience working in both manufacturing and distribution companies, and he has experience that spans from procurement, sales, and management. Now, allow me just a moment to share a bit about IWC, especially for those of you who may not be familiar with our organization. For more than 55 years, we've been an entrusted partner to thousands of companies spanning manufacturing, infrastructure, broadcast, and telecommunications. We are an employee-owned company. We have over 30 locations in 11 countries, and we serve customers in nearly 100 different countries around the world. Now, before I turn things over to Matt to begin the presentation, please allow me just a moment to share a few logistical details to ensure the session runs smoothly for each and every one of you. But first of all, we are recording this webinar, and we're going to make that available to all of today's attendees so that you can revisit the content at any time. So keep your eyes peeled for an email over the next few days to let you know when that's available. Secondly, to ensure a good audio experience for everyone, we have muted the phone lines for everybody but our presenter. So I would encourage all of you to make use of the questions window you'll find on the right side of the webinar to submit your questions. And that way you can reach out to the IWC team at any time throughout the presentation. Lastly, this is a live webinar, and we will be offering a question and answer session at the end of today's call. So as I mentioned, with the phones muted, we will have you submit your questions through that chat window on the right. So no need to wait till the end to ask your question. If anything pops up at any point during the presentation, go ahead, share it with us through that chat window. We'll get through as many questions as we can on the call. And if by chance we run out of time and are unable to address your specific question, rest assured, because each and every Q&A submission will get a direct response from the presenter via email. All right, enough logistics. Let's get started on the presentation. At this point, let me hand things over to Matt to walk us through the details of today's topic and the agenda he has prepared for you. Matt?
Well, all right. Welcome, everyone. Glad to have you here. Let's just jump right in. Wire and cable. So let me just give you some things that often come up with folks new to the industry. What's the difference between wire and cable anyway? Why do we have to call it wire and cable? And the truth is there's practically no difference whatsoever. When most folks say wire, they're talking about something little, and cable is something big. For those people who get kind of techie about it, wire would be a single conductor, whether it's insulated or not. And cable would be a multi-conductor, maybe like an extension cord where you have 3 conductors that are all put together. But the truth is, wire and cable, those words are used interchangeably. So don't let anybody look at you cross-eyed if they say, no, that's really cable. It's not wire. You just tell them to sit down and be quiet. So, another question: why does the wire size go up a number, but the actual size gets smaller? 18 gauge is actually smaller than 16 gauge. What the heck is up with that? It is the nature of wiring cable, of the conductor size, and this goes back a century. There were two American guys by the name of Brown and Sharp, who said, what we're going to do is we're going to number the conductor by the number of processes it goes through. Now, copper stretches like a rubber band, and typical copper is purchased by almost every manufacturer in the world, actually, in copper rod, which is 5/16 inch wide. It's about the size of your pinky finger. So if you look at your little finger, that's the size of the copper rod in a long length that everyone is buying. Well, if you take that copper, it stretches like a rubber band. Like I said, the manufacturer will take that copper rod and jam it through a diamond die. Diamonds because it's very, very hard, and the copper is softer than the diamond. And let's say, just for clarity purpose, that they're going to put it through a die that's 4/16 inch wide. So the copper itself is 5/16 inch. You push it through a 4/16 inch hole. When it gets through the hole, you pull it through the other side, and it's a little bit thinner. So now it's 4/16 inch. Let's run it through another die. This one that's 3/16 inch. You push that through that die again. You get it through the other side of the die. You pull it again, and it's a little bit thinner. It was first 5/16 inch, then it was 4/16 inch, then it's 3/16 inch. Let's just do that one more time. We're going to run it through another die, and now it's 2/16 inch. Well, it went through 3 dies, and so that cable would be called a 3-gauge conductor because it went through 3 processes. So a 2-gauge conductor only went through 2 processes and is bigger than the 3-gauge. So I've really oversimplified it, but you get an idea. The number of dies it goes through became the number of the gauge size, and that's the reason why the gauge size number goes up while the physical size of the conductor goes down. And this only happens here in North America, only in the United States and Canada. We use the AWG system. That's the American wire gauge system. And so we're kind of different from the rest of the world. Our numbers go up, the conductors go down. In Europe, it's the opposite. They measure the size of the conductor, and as the conductor gets bigger, the number of the conductor gets bigger. So it's an American thing more than anything. So, and what about fiber optic? I'm going to touch on this just at the very end. Fiber optic is different from copper conductors, and we'll go through that in a little bit. So let me just talk about the agenda. Really, this is the basics. This is for folks who are new to wire and cable, so the purchasing folks and the sales folks. Engineers, for the most part, have all the knowledge that I'm going to put forth here. I might have a few little things that might interest the engineers, but it's really for the most basic of electricity, and then how that electricity is called out in amps and volts, and then what are some wire and cable applications. So let's just jump right into electricity. So mostly what IEWC is selling is electric cable. We sell a little bit of steel cable, which is used for strength, you know, to hold a pole up, for example, but I'm not going to talk about that at all today. Our wheelhouse, where we do most of our business, is electrical cable. And electric cable has 2 primary functions. I'm going to hammer on this throughout the presentation, so I hope this is something you take away after I'm done with the presentation. And what are those 2 primary functions? Number 1, electric cables allow electrical flow. They make things go. Turn on a light, turn on a toaster. They make the cable is connected to your stove, so you can heat up your stove and bake a cake. It's going to turn a motor so that the fan will blow air. It's all about making things go. That's primary function number 1. The second primary function is a little different. It's about data transmission. It's about moving a pulse down a conductor. When you think about talking on a telephone, that's a good example of data transmission. They have very different uses, and as a result, the design of the cable is going to be quite different. All right. So, but first, before we get into the parameters of what that cable looks like, we need to learn just a little bit about electricity, the basics of electricity. All right. So, ever heard of static electricity? Everyone's lived through this as a child, right? You take your shoes off and you're walking across a carpet in your stocking feet. You touch the doorknob and kablam! You've just discharged all that electricity built up on your body, and it's all flowed out of you and into that doorknob. And you do it at night. You can literally see a spark fly from your body to the doorknob. Well, that's static electricity. That's all about a buildup of a charge that eventually gets discharged. But cable is usually used for dynamic electricity, for flow. It's all about how do we get the electricity to move through a circuit. And of course, here's just a simple picture of a circuit where you've got 2 batteries, which will provide the initial power, a switch, which opens and closes the circuit, the lights, which are going to light up, and of course, the wire, the cable, the wire that's going to carry that electricity through that circuit. Well, what function then does that cable or that wire, as we just saw, what true function is that serving? It's only serving one function. It's carrying the electricity. That's all. It's just a road. It isn't adding anything to the circuit other than carrying it from point A to point B. So, I said that the cable will heats up the toaster, but it really doesn't. It's just carrying the electricity from the wall to that bank of resistors in your toaster, which heats up and then makes the toast brown. It really isn't cooling the air in your conditioner. It's your air conditioner. It's just carrying the electricity to the compressor, which is compressing the air, and eventually that turns into the cool air. It isn't making your light bulb go. All right. It's all about flow. It's just about carrying the electricity. So, all right, how does it do that? How does it carry that electricity? Well, before I want to do that, we need to jump into something else. And what is that? We need to jump into amperage and voltage. Just get a basic understanding of amps and volts to understand that flow. So, different appliances require different amperages. All right, so let's talk a little bit about it. But first, can you tell me, please, what the heck does an amp, what does amperage mean? What is an amp? So an amp is simply the quantity of electricity that is flowing. And the analogy I'm going to use, it's the most common analogy when it comes to electricity, is like water. It's 20 amps of electricity is like 20 gallons of water. When you hear amps or amperage, it's all about quantity, how much electricity is flowing through that circuit. So I've got a few examples here. A light bulb is going to pull just under an amp. A 100-watt light bulb is going to pull 9/10 of an amp. Your microwave at home is going to pull about 4.5 amps. Your vacuum cleaner, 7 amps. Your dryer, 11 amps. So how often have you been at home? You've got the lights on, you turn on your vacuum cleaner, and the lights dim for just half of a second. And the reason that's happening, the vacuum cleaner and your lights have the same number of volts. They're still running at 110 volts, but that vacuum cleaner is drawing a lot of electricity. And so for just a second, that light bulb is going to dim as so much of the electricity is being used to run that vacuum cleaner. In fact, the volts go down just a little bit. That's why the light bulb dims for just a second. Then it goes right back up to 110 volts. All right. So different appliances use different quantities of electricity. The other part of this is, where is that electricity coming from? What's the source of that electricity? Well, different sources of electricity have different voltages. So, oh yeah, all right, great. What's a volt again? So a volt is the unit of force moving electricity. All right. Before I was talking about quantity, so 20 amps is like 20 gallons. In the case of water, it's more like PSI. How hard is that water coming out of that? It's coming out of that hose. It's not measuring quantity. It's measuring force. So the more volts you have, the greater the force. So let me give you an example. If you've got a flashlight, you've got your batteries there, that's 1.5 volts that those batteries are putting out, which is not a lot of voltage. And anyone who's touched both ends of a battery, you don't get a charge at all. You're just fine. It's safe. You can touch a 9-volt battery. You put in your smoke alarm. Again, that voltage is not unsafe. By the way, our bodies can resist about 24 volts. So that's the reason you don't get a shock, because we're actually resisting. There just aren't enough volts to flow through us. Don't test that. By the way, please don't test that, but that's just it's just a little tidbit. So our cars are running on 12 volts of power, so a little bit higher than a battery using a flashlight. And then, of course, anything you plug in the wall here in North America is at 110 volts. In fact, it's 125 volts, but we say it's 110 volts. And then if you go to Europe, they're actually running at higher voltage. Europe is running at 220 volts. Actually 250 volts, but they're running at a higher voltage than we are in North America. There are advantages to having higher voltage. There are disadvantages of having higher voltage. It all depends on the application. So this is something that comes up quite a lot in the question of wire and cable, is what's the operating voltage that we're talking about, all right? So different sources of supply run at different voltages. different appliances run at different amperages. They're drawing different quantities of power. All right. So let's move on. So an important concept to take away today is just that when you put force and quantity together, put volts and amps together, that's going to measure power. Now, in the electric industry, we call power watts. So the most common example everyone thinks about is a light bulb, a 100-watt bulb. It uses 100 units of power. It uses 100 watts. It's 100. So it's power that when you talk about watts, we're talking about power. We're not talking about quantity of electricity. We're not talking about force. We're talking about the power usage. All right. So here's the equation: volts times amps equals watts. It's called Ohm's law. Force times quantity equals power. If you remember, volts are force, amps are quantity, and watts are power. All right, you might see it expressed that way: volts and amps is watts. Sometimes the amperage is configured as the letter I. So anyway, volts times amps equals watts. And so in the case of a light bulb, for example, there's 110 volts coming out of your socket at home, and it's using 0.9 amps, so that comes to 100 watts. All right, volts times amps equals watts. That's the amount of power. That would be a good takeaway from today, if you can just carry that around in your head. All right, so volts, amps, watts, does it really matter? Well, when you're talking about wire and cable, it does. If you're talking about wire and cable and why we use this cable, why we use that cable, this is where it really begins to become important. So let me go back again. If you want to make things go, what is the cable doing again? Well, it's providing electrical flow. It's providing electrical flow to make that motor spin, to make that light turn on. So that electrical flow then, whoops, there we are, just technical difficulty. There we are. Oh, I'm sorry. And the second thing that wiring cable is doing is also transmitting data. All right, and I'm going to get to that in just a second. So that electrical flow then is all about running through the entire circuit. Now, if the circuit is a chain, from your experience, what is the first link that breaks in the chain? I don't care what that chain is. If it's made out of steel, if it's a chain of events that happen, what is the first link that's going to break? Well, it's the weakest link, isn't it? The weakest link in that chain is going to break. And so wire and cable can be that weakest link if you don't size it right, if you don't get the right size of the conductor or the right insulation. So it's all about getting the proper size for voltage and amperage to make sure that the cable itself is not the weakest link in that circuit. All right. And what is that? It's all about quantity. It's all about force. It's all about amps and voltage. So when you talk about wiring cable, you're just going to hear about over and over. What are the amps that we need? What's the voltage we're running at? All right. So those are the two primary factors when you're talking about making things go. So, all right, we've got a use, and it's going to require more amps. Typically, we need 20 amps. You know what? We need more amps. How are we going to get more amps through the cable? Well, what do you do when you need more water? Well, you get a bigger bucket, don't you? So with cable, it's just the same. Maybe you need a bigger cable. So let me give you an example of how conductors are rated. This is per the National Electric Code. This is a 100% factor for any engineers who might be on board at 90 degrees C. So 14 gauge is allowed per the NEC to carry up to 25 amps. 10 gauge can carry more. It's a bigger conductor, can carry more amps. 6 gauge more, and then 2-aught, which is bigger, by the way, can carry up to 190 amps. I'm just trying to illustrate here that when you need more amperage, you need a bigger conductor. You need more water, you're going to need a bigger bucket. All right. What about voltage? Voltage is about force. It's not about amperage, or it's not about quantity anymore. If you're going to have more force, you need a bigger force field. You need something that can contain that greater force that conductor is going to be, that's going to move down that conductor. It's like having extra pressure in a hose. In this case, we have a garden hose and a fire hose. So fire hose is designed It's got a stronger wall. It's probably bigger. And so we do the same thing in the wire and cable, and we will adjust the insulation. You're going to have a bigger force field. And let me just walk through an example of that. I'm going to put out a sample of a single conductor cable. It's called UL1007, a very simple thing. It's used at 300 volts. It's just copper, and it's got insulation around it. And you can see it's 15 1/1000ths of an inch thick. That's how much PVC is surrounding that conductor. Doesn't sound like a lot, and it really isn't a lot, by the way. That's, if you look at a piece of paper, that's 4 1/1000ths, so that's 4 pieces of paper thick that goes around that conductor, and that's rated at 300 volts. So you can run 300 volts power through there. The very same conductor, very same. This is a different UL designation. It's UL 1015. If you want to run 600 volts through it, you've got to double that size. Now it's got to be 30 1/1000ths of an inch. By the way, in the electrical industry, we call it 30 mils or 15 mils. If you ever hear that, mils, all it means is milli-inches. It means thousandths of an inch. So in one case, 300 volts, it's 15 mils, and 600 volts, it's 30 mils. So you take a look at those two conductors, the only difference is how thick that insulation is. Everything else is the same. Conductor is the same, the insulation type is the same, but we've made the insulation thicker to carry a larger voltage. Now we can also change the insulation. There are some insulations that can be rated for 600 volts. That's the same size as that 300 volt, but it's all about polymer science today. I'm just keeping it simple and saying that very often, if you're going to, not always, if you're going to go to a bigger voltage, you're going to go to a bigger insulation, or you change the insulation entirely, by the way. All right? Okay, so volts and amps are what I hope you walk away with today. It's really what you need to know. There are other things too that you're going to need to know eventually, and those can come in future training sessions. Here are just some examples: the resistance of the conductor, the capacitance, velocity of propagation, attenuation. But you know what? That isn't today. Those are important concepts, and those will come in future sessions, not today. Okay.
All right. As Matt's getting ready for the next section, probably a good spot just to remind everyone, if you have questions, no need to wait till the end. Go ahead and use that chat window over on the right side and drop those in, okay? All right, thanks, Matt.
All right, you bet. And if I'm going over concept too quickly and someone wants to ask something, go ahead and jump that question in there, and we'll be happy to answer it or to address that question as we move on. Okay, so you remember I said that the primary function of cable, there are two of them. One is make things go, to turn on the light, to heat up a toaster. The second thing is all about transmitting data. This is just an example of it's going down, data is moving down a tunnel here. So here's what I'd like you to think about when you're thinking about transmitting data. Imagine the first common way that we used electricity to transmit data was the telegraph about 150 years ago. And when you're transmitting, when you're using a telegraph, well, you're taking advantage of every electrical conductor when you run power through it, throws out a magnetic field. I don't know if you remember this from fourth grade or not, electromagnets. Remember, you pull a chain of paper clips across the table. Anyway, it was all about energizing something, and then there was a magnetic field that would come with it. Well, the telegraph operator, let's say he's in Chicago, he's going to push a hammer down, and the electricity is going to flow all the way to New York. And in New York, it's going to pull down a hammer that the telegraph operator in New York is watching. That's a magnetic pull that's happening. And so it goes up or down, right? It's either an open circuit or a closed circuit. It's a dot or a dash. All that operator's doing is closing and opening the circuit. Close and open, dot or dash. What does that mean? Well, it's like saying yes or no, isn't it? So that operator in New York is like, okay, I just heard it happen quickly. That's a dot. Oh, it happened slowly. That's a dash. It's like a 1 or a 0. And you know what? Our data cables today act the exact same way. When you think about data cables, like an Ethernet cable you're using in your computer that hooks up from your computer to your monitor, or between computers, all that's doing is flowing a yes or a no, a 1 or a 0. It's flowing. There's a lot of data going back and forth, but that's all it's going. So all of our circuit boards work off of this. Our cell phones work off of this with cellular technology. All of our digital entertainment, you know, you're watching a high-def TV. That's all it is. It's just a series of ones or zeros. That's it. So I'm going to go into this just a little bit so you can begin to understand why this is important. It's all about a pulse. So when you're talking on the phone, let's not use a cell phone. Let's use an old analog phone, the kind I grew up with. It's a pulse. I would talk, an electrical pulse would move down that line. And sometimes that pulse would be big if I was speaking loudly, so it would be amplified, or it'd be smaller if I was whispering. If you sing, that pulse is going to go up and down, but it's still just a pulse. It's just a bit of data, an electrical pulse that's moving down that conductor. All right? So the intensity can go up or down, but that's all it is. It's just a blip that's moving down the conductor. Well, when it comes to moving that pulse up and down the conductor, there are two primary concerns that we have with regard to cable. Number one, how quickly can we move those pulses down the conductor? Now, a telegraph operator, a good one, could move about 4 times a second. He could get a dot or dash out about 4 times a second. The guy on the other end could read 4. So that was 4 bits of information. How many bits are moving down your Ethernet cable right now? When the fax came online, boy, this was revolutionary when it hit like 1987. You could talk to each other by fax. That was moving about 10,000 bits a second. So that fax computer, I don't know if you ever remember those annoying noises. Those fax machines would make and then it put out annoying sound. That was about 10,000 bits a second that it was transmitting, so that you could print the letter A and then the letter T next to it and then a space. Well, today our Ethernet cables, a Cat 6A cable, is moving 16 trillion bits of information a second. All right, that's a lot of data. That's a lot of information moving down that conductor. So you want speed. Why do you think you would want speed? You want speed so you can send more data down. That way, instead of just a fax where it's screaming a little bit of information in time, you can now get a video signal down that line, or you can get a high definition video signal down that line. So when you're watching the PGA, you can actually count the number of dimples on that golf ball. So the speed is all about transmitting a lot of data quickly. The second thing you really want to be concerned with is the clarity of that transmission. How clear is that data being received? Does it get scrambled as it moves down that conductor? And it can get scrambled if there's a lot of noise in that cable, if there's a lot of noise in that circuit, electromagnetic interference. So I'm going to talk about that in just a second. So when you're thinking about data and communications, think about speed and the clarity of transmission. Some common problems with clarity are crosstalk. That's when one conductor's data will, a shadow of it will literally jump into the conductor right next to it, and then that other conductor gets cluttered with data that you really don't want in that conductor. Interference, electric or magnetic interference. A perfect example of that is I remember when I watched TV as a boy, my sister would turn on her hair dryer, the television signal would get scrambled because that hair dryer was putting out electromagnetic interference and was interfering with the signal that was coming across the antenna. Or you can have electrical charge buildup, and that's that some conductors are not good about moving all of the electrical charge, and they wind up storing some of it. That's called capacitance, and it can be a real problem. So there's some solutions to clarity right now, and these are ones that you're going to run into as a salesman or a purchasing agent. One is if you twist the conductors, you can get rid of that crosstalk that I was talking about, where a signal jumps from one conductor to another. So you'll often see that the twisting, they say it's got to be an inch or smaller. That's the reason they're calling out the number of twists in a conductor. The more twists, the more clarity. Unfortunately, the more twists, the higher the cost. Or you will shield the conductor. And that's really good for electromagnetic interference. You'll see a cable that say you need a shield going over it, whether it's aluminum mylar or whether it's a braided shield. That's all about catching any electromagnetic interference and running it to ground. Or you can use different insulations. Typically, the more an insulation blocks out interference, the more expensive it becomes. And there are all kinds of ways of doing that. And some of them become quite pricey, which is why you might see an FEP, a Teflon insulation, like, holy mackerel, that's expensive. Yeah, but we're transmitting important data, so we're going to use an expensive insulation. All right? So with the two primary functions of cables, if you remember the two primary functions, guess what the very first question is that you need to think about as a salesperson or as a purchasing agent or an engineer? The first thing, is this for power or is this for data? Because they're different, aren't they? If it's for power, oh, excuse me, I'm going to move on and I'll return to that thought. So is this for power or for data? And often the name of the cable is going to give that away, all right? So if you hear control cable, the customer says, I need a control cable, he means power. That's what he's transmitting. As soon as you hear control cable, you can think power. And you learn this over time. Or he's going to say, I need instrumentation cable. What does that mean? Well, he's transmitting data. He's not transmitting power. So power is about volts and amps, and data is about clarity and speed of transmission, right? Different requirements. What if he says power cable? Well, you're in luck. You already know what that's about. What if he says data cable? All right, things are getting easy. Communication cable is typically where they're transmitting data, so you're worried about speed and clarity. But if he says it's going to be an industrial cable, all right, you got to slow down, so pump the brakes. I need to know which one this is. Is this about power or is this about data? Because they lead down different sets of inquiry, all right? So I just wanted to touch on fiber optic cable. I told you I'd do that. So fiber optic is just another kind of data cable. I was talking about data transmission, and fiber optic is no different. It's just transmitting data. But what the only difference, and it's a big one, is that it's not using copper, it's using glass. And it's not electricity that's running down that conductor, it's light. So it's pulses of light as opposed to electricity, which means if you touch fiber optic, you're not going to get electrocuted, but if you look down a fiber optic cable, you'll go blind. So you really have to just have an understanding that this is a different animal, but its function is similar. It's transmitting a pulse down a conductor. The conductor in this case is glass. All right? And quite literally, that pulse is moving fast. How fast is it moving? Well, it's moving at the speed of light. Than that, right? E equals mc squared. This is so light moves faster than electricity. Light does not slow down. There can be interference in the conductor. It might be cloudy. There are other problems, but largely it's moving fast. So the advantage then, well, I'm getting ahead of myself here. So you're just not going to get faster than the speed of light, and that's why people want to use fiber optic. So the advantages of fiber optic are, one, the speed of transmission. And if you remember, the speed of transmission means you get more data per second moving down that conductor. So almost all high definition video today, if you're watching an NFL football game, they're shot in high def. They're shooting that through fiber optic cables, because the fiber optic cables can move more data than a typical electric cable can. And then, of course, that's being transmitted digitally through the air, or through your cable conductor is being transmitted digitally to your video at home. All right. Well, that sounds pretty great. Why don't we use fiber optic all the time? That sounds great. Well, number one, connections are doggone expensive today. So whenever you're trying to connect fiber optic, those connectors are expensive and they're troublesome to do. So it only makes sense if you're running long distances. If you're running short distances, the connections are so expensive that using electrical transmission makes more sense. All right. So fiber optic is good sometimes and not good other times. So remember, and here's the wrap up for the presentation today. This is really what I hope you can take away. When someone's talking about power, what they really want to know is what is the size of the conductor they need and what's the voltage they're going to be operating at. Those are the two things that you as a salesperson or a buyer need to understand when they're talking for a power cable. And if someone's talking about data or communication cables, you need to understand about speed and clarity. It's not about power. It's less about voltage. Voltage comes up a little bit, but it's about speed and clarity. How quickly do you need to move this transmission? And then what are the clarity requirements around that? All right, that's about it. That's the end of the presentation today. If there are any questions or you have any feedback, it'd be great to get them now.
Perfect. Thank you, Matt. We've already had a few folks chime in with a few questions using that chat window over on the right. If you've had a few that you've been noodling on and would like to hear Matt's thoughts on, please feel free to do so as well. So, Matt, thanks so much for sharing your insights and providing some real helpful nuggets, helping us all get a better grasp of the basics of wire and cable. Matt, kind of somewhere in the middle there, indicated there's an opportunity for future topics. So if that's something of interest to you, you kind of like to learn more in this area, there's going to be a survey coming out at the end of this. Great opportunity for you to let us know, hey, saw a lot of value in this, would like to learn more, and this type of format really helps. So we look forward to hearing your feedback that way. Now, as promised, we have carved out a bit of time here at the end to do a question and answer session. Now, throughout the presentation, a few of you have submitted questions, and once again, we might not have the opportunity to address every question live here on the call, but every question submitted will get an answer from our presenter. It may just be in the form of an email afterwards, okay? Now, as Matt's taken a moment to review the questions that were submitted, because he was a little bit preoccupied the last few minutes, talking through what he wanted to share with you, let me take this opportunity. I want to encourage you to explore the all-new IWC.com. There's some real exciting enhancements that went live just earlier this month. For the first time ever, for example, we now have the ability on IWC.com for customers to be able to order online with pricing and transaction history right there for you. And there's so much more in terms of what's been added and growing on our site. One other thing I want to make you aware of is I'm excited that you're going to be the very first to hear about this. We've got a new ebook that we've just published, and it's entitled What Every Purchaser Needs to Know About Sourcing Wire and Cable. So if you found value in today's webinar topic, I'm guessing this may be a really convenient resource that you'd be interested in as well. So as a result, what we're going to do is when we send you out that follow-up email, giving you access to the presentation and the recording from today, we're also going to give you instructions on how you can download this ebook as well. So keep your eyes peeled for that email from IWC, okay? All right, enough about us. Let's get to your questions. Matt, you ready to jump into a list of questions from our guests?
Let's go.
Okay, excellent. So the first one here we had was, does wire gauge affect the distance data or power can travel, or is it really just about the level of power?
Yeah, so actually you've hit on a really important concept here, and the answer is yes, it does. The gauge size does affect the distance that the data or power can travel. This when you're in a direct current circuit, a DC circuit, the longer you go, the more power you lose. It's actually called voltage drop. And it's just so interesting. This is where Edison and Tesla got into an argument with each other. Edison said, doggone it, we're going to use direct power, or excuse me, DC power only, because it's easier to produce and it can run at the local level. And Tesla said, no. If we with AC power, the alternating current power, we can hold voltages much better. So and they got into quite a disagreement. And so today it's all AC in our. Anyway, to answer your question, the bigger the gauge size, the longer the power can travel, and the longer the voltage will stay in place, but it will dissipate over time. Larger conductors have a lower voltage drop than a smaller conductor. So if you're in a DC circuit, and it happens a lot, the conductor size matters a lot depending on the length of the circuit. So very, very good.
Excellent. All right, Matt, we've got a few more questions here. A few here that we got were in regard to when you're educating us about gauge size. Two of them that came up. One was, why does the AWG only seem to be listed in even sizes? And then what did you mean when you said it was 2/0 or 3/0? What did that mean relative to some of the other values you shared?
Yeah, so if you look, you see AWG always comes up in even sizes. The truth is there are odd sizes as well. It's just an industry standard, that's all, that you jump through even sizes. But every once in a while you're going to someone's going to say, I need a 9 gauge. Doesn't happen often, but it does happen. And a good example is when you go home, take a look at your vacuum cleaner. More and more vacuum cleaners are now using a 17 gauge on their conductor. So now I'm a wire geek, so I read every piece of wiring cable I see. But if you go home and you take off you look at the cord, it's printed on that cord, the size of that conductor. And especially vacuum cleaners, you'll often see a 17 gauge conductor. But it's mostly just convention. We go even number sizes, but odd numbers are out there. And then you asked about the 2/0, 3/0, 4/0 size. Here's just another goofy thing about our nomenclature, why we use these numbers. When Brown and Sharp started with their very first gauge size, they started at 0. And if you went through 1 die, that was a 1 gauge. You went through 2 dies, that was a 2 gauge. So they had everything on a conductor going from 0 all the way down to like 54 gauge. So it gets pretty small. They didn't have anything going bigger. So after 0, they said, well, we need something a little bit bigger than 0. And he said, okay, we'll call it 0, 0. All right, we need something bigger than that. All right, we'll call that 0, 0, 0. Said, all right, we still need something bigger. They said, all right, 4 zeros, and now we're going to stop. So rather than see the nomenclature 4 zeros in a row, you'll see it called a 4/0, which is typically called 4/0. Or you see 3/0, which is smaller than a 4/0, and that's called 3/0. And after 4/0, they just stopped. And then the nomenclature changes to the size of the conductor. You'll see a 250 MCM, so that's bigger than a 4/0. You see a 400 MCM, that's bigger than 250 MCM. So once you get into the big sizes, the larger the size, the number goes up. Just the opposite of the AWG. So.
All right. Thank you, Matt. We have one more question that came through. If we have a minute here to hit this last one. If the voltage in the US is 110 volts and in Europe is 220 volts, does that mean Europe uses less electricity to run their appliances?
Yeah, it's just a great question because the answer is yes. Europe is using less electricity. A 100-watt light bulb uses 0.9 amps here in the United States. In Europe, it uses half that, 0.45 amps. So the advantage in Europe or any system that's using 220 volts is you're literally using less amperage, using less electricity. Now there's a cost associated with that. Running higher amps is more expensive. It's more expensive to create. It's more expensive to transmit. The more voltage you use, the faster it leaks out of the conductors. So there's always a trade-off between using 110 volts or 220 volts. And that's why there are two different systems across the globe. If you go to Europe, they use 220. You go to Asia, some use 220, some use 110. Here in North America, it's all 110. In South America, it's largely 220, but you'll run into 110 every once in a while. Africa is a jump ball. You never know what you're going to get. So, but to answer your question directly, higher voltage means you use less amperage, less electricity. Okay.
Okay. Looks like we've got time for one more question here. So let's go ahead and do that. And actually, the one that came through here right under the wire. So are all twisted wires used for communication and data, or are some twisted wires also used for power?
Yeah, so you will see twisted cables used in power. It does happen. It's more typical. It's going to be used in data and communications. The reason that you would twist over on a power cable, usually, not always, but usually, is so you get greater flexibility in the cable. The more twists you have, the more flexible the cable becomes. And so someone might need a very flexible application. Maybe they have a tight bending radius inside an electrical box. Maybe it's being flexed, hundreds and hundreds of times. So you want it to be more flexible. But generally, when I see a twist, I'm generally thinking data cable. But also, yes, it's used in power cables.
Okay. We had one more Sneaking under the wire. I think it's a pretty short answer. So let's get this one as well. Last question here we have: is there a difference between spiral stripe and longitudinal stripe?
There is. In terms of functionality, there's no difference whatsoever. The reason that someone would use longitudinal stripe is because it's made at the time of production of the cable. So as the PVC or rubber or Teflon material is being made, you're extruding that over the conductor, and you can extrude the stripe in at that moment. So say you're going to run a large quantity, 100,000 feet. If you extrude it then, that's the cheapest way to make that product. But suppose that you need a smaller quantity, say 1,000 feet. That's just way too expensive to extrude. So instead, you have the finished product with no stripe on it, and now you're going to attach a spiral stripe on it. The spiral stripe is easy to apply for short distances. And the spiral, literally, the die that's adding that stripe is just moving around the insulated wire as it goes through a paint application. So is there any difference? Not functionally, no. And so you see longitudinal in large quantities and spiral in small quantities.
Okay, excellent. Well, hey, that's all the time we have for today's call. Thanks so much for the questions. Certainly helped us make sure we did a good job of addressing what was of interest to you today. So thanks again to all of our valued customers and partners who joined us today. And of course, thank you as well to our presenter, Matt. Hope you found this to be practical and informative, and we really would value your feedback in the form of an online survey. It's going to pop up and be available to you immediately after this webinar session closes. And one more time, please remember, watch for that email in the upcoming days, because we're going to share with you the recording and the presentation from today, as well as a link to download that new ebook that we discussed. Thanks again for your time. We hope you have a great rest of your day.